I am.
Okay.
All right. All right, everyone. This started recording, so we're beginning. The speaker today is Axel from Heidelberg. He's an expert in gamma rays and also in applying analysis methods and building out software systems to do this gamma ray astronomy. So, Axel, take it away.
Thanks a lot for the introduction. I'm gonna continue on this just a little bit. So I have one slide introducing myself a bit more in detail. Can just confirm that you can see my screen?
Yeah.
Okay, perfect.
Yes, yeah, we can.
Okay, so my name is Axel Donath. I'm currently a postdoc at MPIK in Heidelberg. During my PhD, I mainly worked on an observation program called the H.E.S. Galactic Plane Survey. And there I've mostly worked on the catalog, so extracting a source catalog out of the data. And out of this work, a new software package evolved, which is called GammaPy. And now I'm one of the lead developers of the GammaPy package. In general, I'm interested in the galactic gamma ray source population and methods like for source detection and catalog production in general. I also have a general interest in Python-based astronomical software. So, for example, I've co-organized the Python and Gamma Ray Astronomy meeting in 2019. And I also have contributed to the AstroPy package, which I think by now is currently very, very well known. I've put a link to my GitHub profile there just to summarize a bit my software work. In general, thanks a lot for the invitation and the opportunity to present my work to a group. Thanks a lot. I decided to put a little preface just on my talk. I call it for X-ray astronomers, but also for everyone else. So in general, I think like many analysis methods that we use in gamma ray astronomy are actually inspired from X-ray astronomy. And also, I think like in general, the structure of the data is very, very similar. I mean, it's counts-based data. It has Poissonian nature and statistics. And one is required to handle somehow the instrumental response and has to deal with effects like limited angular and energy resolution, as well as like a non-uniform exposure and effective detection area of the instruments. In detail, of course, the structure of the data is certainly different. I think this probably mostly concerns like the complexity of spectral and spatial features, which I think in X-ray astronomy is like way more complex than in gamma ray astronomy. And then also, for example, in gamma ray astronomy, I think there's still like, at least for ground-based instrument, there's still like always the limitation and the challenge to handle the residual hadronic background, which basically dominates all the data that is captured by those instruments. The standard statistical analysis method in gamma ray astronomy is binned maximum likelihood fitting. I mean, what I'm going to present in this talk does not go beyond this, but it shows like a generalization of this methods to more dimensions. So taking into account spatial and energy dependence of the data. So in that sense, I'm not going to introduce, let's say, any new groundbreaking statistical method, but really like this generalization of the methods, and also like how to provide these standard methods to a larger community of science users. Here's a quick overview on my talk. So I'm going to just start with the H.E.S. Galactic Plane Survey, just as a scientific, but also a general motivation for the data analysis methods. Those then I'm going to introduce after, and then I'm going to quickly talk about the GammaPy package, and then give a summary and an outlook of what is to be expected, and things that are currently being worked on. Okay, let me start with the H.E.S. Galactic Plane Survey. This is just one little slide as a reminder on what kind of instrument the H.E.S. observatory is and how does it work. So H.E.S. is an imaging atmospheric Cherenkov telescope. And the working principle is that a gamma ray enters the atmosphere and then triggers a particle shower in the atmosphere, and it triggers an electromagnetic cascade of secondary particles. Those secondary particles typically move faster than the local speed of light, and then it produces like a flash of blue Cherenkov light. And these are very short nanosecond lasting flashes, and those can be observed by optical telescopes from the ground. typically using like photomultiply cameras that are then positioned together with a telescope in the light pool. If this is done with multiple telescopes, then the energy and arrival direction of the incident gamma ray can be reconstructed, and such like can be reconstructed. And typically the instrument is pointed then for a given period of time on a certain position on the sky, and then just starts measuring events. And this is called, just to introduce the vocabulary, an observation or an observation run. In the H.E.S.S telescope had, it's short for the high energy stereoscopic system, and those are located in Namibia, and it's an area of 5 of those imaging atmospheric Cherenkov telescopes. And they conducted an observation program which lasted from 2003 to 2013, and it included 6,000 of these pointed observations to actually survey the galactic plane in TeV gamma rays. And this corresponds to roughly 3,000 hours of observational data. The energy range covered by those measurements were between 0.2 TeV up to roughly 100 TeV. In fact, it only covers the small part of the sky, but it's already known that like most of the expected high energy sources, for example, from the Fermi-Lat telescope, are actually located in this region. So it covered most of the expected emission. I think what's already obvious, so the survey region is illustrated on the left side, and I think what's already obvious is that really the Milky Way is bright in TeV gamma rays. Just a bit more details on this figure on the left side. So what you can see is an all-sky image of Planck CO data, just to illustrate a bit the structure of the galaxy, and then the white box shows the region surveyed by the H.E.S.S instrument, and then the zoom in actually shows then the measured flux in TeV gamma rays, measured in percent of the Crab flux. So the Crab is used as a standard candle in gamma ray astronomy for the fluxes. And as you can already see, really like the Milky Way is very, very bright in TeV gamma rays.
Question. Oh, by the way, I don't know if Anita warned you, Axel,
yes.
We interrupt almost constantly. So with questions. So I have a question about this observation time strip down here on the left. Why are the circles? I mean, I figured that this being a ground-based telescope, you should see large parts of the Milky Way at the same time, right? And why is it blobby?
Yes, I mean the field of view of these instruments is limited, and typically the field of view is roughly a circle of diameter of 5 degrees. This is typically what you see. As I said, I mean, like the optical telescopes, I mean, they don't observe directly the universe, right? But what they do is they use the atmosphere as a scintillator for a particle detector. And then they observe the gamma ray showers. And what you typically get with these kind of instruments is a field of view of 5 degrees. And so like these individual circles that you see on the observation time are really like these pointed observations where the instrument was pointed for typically half an hour on this exact location on the sky. And this is why it looks like the distribution of the observation time basically looks like this and has these circular patches.
So, but there was no effort made to smooth it out. I mean, to make it flat, or was it not possible because of weather or something?
This could be improved with instruments that have a larger field of view, and I think the way to achieve this is to build an even larger array of telescopes. And this I'm going to talk a bit about later. So there's already like a next generation instrument of these imaging Cherenkov telescope, which is called CTA, or the Cherenkov Telescope Array. And there the field of view will be roughly 10 degrees. So the field of view will be already larger.
No, I mean, beyond just the field of view being larger, I mean, typically what we strive to do is to make as flat an exposure map as possible, right? And the fact that it is so, what's the word, bumpy, makes it harder to do the analysis, right? I mean, it's
yes, partly. I mean, What I can tell already, I mean, if you look, for example, can you see my cursor?
Yeah.
I think as a red dot. If you look, for example, in these regions, there you can see these are observations where we tried exactly that. So the instrument was pointed in a well-defined pattern along the galactic plane, and to achieve somehow like a uniform exposure. But in addition, of course, there are objects which are more interesting. For example, the galactic center, where you can see like the instrument just spent much more time on the galactic center just to get more and more data on these specific sources. And this makes like the whole thing appear more patchy.
Okay. No, so there is actually a quote unquote important sampling going on, in the sense that you tend to look at the places where there is more flux.
Yes, this is one part of the thing, and then the other part is just covering, let's say, empty regions with a uniform pattern of observations. Exactly.
Okay.
Yeah. But is this like if I wanted to observe, let's say, galactic center, I would just point there, and the circle will just show that I pointed there for like 300 hours, let's say, right? So it's just I understand this one circle as the observation time or observation of this part of the sky. Is it right? Each circle
almost like each circle corresponds roughly to half an hour of observation time, and it's pointed to or centered on an exact position on the sky. And then you have like 6,000 of those circles stacked on top of each other with the half an hour of observation time. That's basically how it's accumulated. As I said, in total, this is like 10 years of data.
Okay, thanks.
Okay, so based on this data set, there was now the goal. I mean, really, the Milky Way is bright in TeV gamma rays. There was now actually a goal to compile a catalog of TeV gamma ray sources or a uniform catalog of TeV gamma ray sources for the first time. And I would like just to quickly explain a little bit what how this worked. So the analysis was basically based on 1D and 2D Poisson maximum likelihood fitting. I'm going to explain a bit more on the Poisson maximum likelihood fitting later, but then in the context of gamma pi and analysis methods. And what we decided to do, so on the left side, you can see the measured count. So it's what we call the axis. So on the top panel, you can see the measured counts from the bind into a sky map. And then we subtracted the hadronic background. And what's left over is basically an axis of the events over the hadronic background. And this you can already see somehow that there appear like different structures, such as supernova remnant or shell-like supernova remnants on the left side. Also on the right side of the image. In between, then there are point sources, and you can possibly already guess that there's maybe something like a diffuse band somehow in the middle of emission. And what we've done to extract the catalog from this was that we decided to model this H.E.S.S as a superposition of Gaussian components. So we made this decision of just saying we're going to represent the axis using Gaussians. In many cases, this works well. So sources, for example, this one here, have what I would call like a centerfold morphology. So they are brighter in the center than they are at the tails. But then there are, of course, already cases where this does not work well. On the right side here, for example, you can see there's something like a shell-like supernova remnant. So actually the morphology of the source appears as a shell. And in this case, of course, like a Gaussian model or Gaussian model assumption just clearly doesn't make sense. And for this reason, we just decided like these sources with complex morphology, this we're going to exclude from the analysis, just because we didn't really have like a good way of treating those uniformly in the analysis. And then the whole data was divided into two smaller regions of interest. Basically one that very similar to the one that I'm showing on the left side. And then we modeled those as a superposition of the Gaussian components. And then, of course, I mean, for Poissonian data or counts limited data, there's always the interesting point is the component or is the emission that you're looking at is significant. And the way to handle this was that we fitted the data with multiple components, and then we added a new component, and then we estimated the difference in test statistics compared to the model with one component less. And then we set a certain threshold on this, basically to prevent overfitting, so to prevent like fitting very, very small excesses, which were not really significant. In addition,
can you just spell that out a little more clearly? So when you're fitting a bunch of Gaussians, it sounds like something like a finite mixture model where you have a Gaussian distribution for the location,
exactly,
events, and then you start with a certain number that seem clear, and you add one. So you're trying to test.
Exactly.
And then you said you compared the test statistic.
Yes, exactly. This I can explain a bit more in detail. Exactly. So it's a superposition of multiple Gaussian components, and then you're looking basically for the Gaussian components can have varying parameters like position, of course, like size, and then of course you're doing the fit to the data, and then you compute it's a bin likelihood fit. And so you compute the overall test statistics on your full data. So you sum, for example, the cache likelihood, you sum it up for all bins. And then you add up with a single, and then you have like a single likelihood value of its statistics value. And this is optimized. And then you add one component more, and then you check like what's the main difference, or what's the difference that you see in the global likelihood.
But what test, you said, test statistic. I don't.
Okay, that's probably just the term that we use. So the test statistic is just defined as the difference between two models, or as the difference like in the total likelihood between two models. But I have to say, like, what I call likelihood now is like it's what we call like the fit statistics in our terms, and this would be like -2 times the log likelihood.
Right. So what you're computing a likelihood ratio test, it sounds like.
Exactly. Yes.
And then how do you determine if that thing is big enough to decide that there's a extra source?
Yes, I mean, we've set this threshold for the difference in test statistics. We've set it to 30, and this was derived from Monte Carlo observations. So the idea was that this threshold would be chosen such that you typically expect like one false detection in the overall survey region.
Okay.
There was one side effect of this choice with the multiple Gaussian components. So the first one was really that, for example, shell-like supernova ramps couldn't be modeled. And the second one was that some of the sources basically decomposed into multiple components. I mean, already now sources are extended in gamma ray astronomy. And if this model assumption does not fit very well, then it would be somehow decomposed into multiple Gaussian components. What we did later by hand basically is just merge those components again and just say somehow they are part of the same astrophysical source. And so we computed then in the end somehow like joined or merged source characteristics for this. What we've done in addition, this is something that was or that has been known, is somehow there is like true interstellar diffuse TeV emission, which shows up somehow as a band in the along the galactic plane. And there we decided just to derive a generic model or an empirical diffuse band model from the data. I think the details of this probably I'm gonna leave out on this. But what we've basically found is that it just stabilized the fit that we were doing with this multiple Gaussian component. And then like this overall axis model, this is then illustrated in the second panel, basically consisted of these multiple models. So we had these diffuse large scale emission component, then we had these cases where like the emission was modeled with a single component Gaussian, then we had these models where it was modeled with a multiple component Gaussian. And then we also found in addition, like typically extended components in the data that were not really attributed to any astrophysical source. It could be background systematics, could be something else. These are called like these discarded components, and we listed those separately and just said, okay, like this is not, it's significant in the data, but it's what we can't make sense of it.
You didn't think that it was dark matter emission?
No, we didn't dare.
Okay.
As I said, I think the likely explanation is background systematics and not fully understood background. And this led then basically to the first or to the estimation of the morphology of the sources. So we could measure the position, we could measure the size, and we could measure the brightness of the components. And then in the second step, for all the sources, we also measured spectra. And the way we've done this is that we've defined an analysis region and then have performed aperture photometry in this region. So we summed up all the axis and flux in the circular region defined by the morphology of the source, and then fitted a power law and an exponential cutoff power law to the source, for example, to see whether really there's a cutoff at high energies for the source. In general, this modeling pipeline was based on the Sherpa package. And I think we'll probably come back, let's say, to these analysis methods and also to the statistics a bit later, in the context then of
Axel, sorry, could you go back to previously? So I noticed the scale over here with the square root T.S. on the bottom lower. And it seems to go from +5 to -5, which is only plus minus 25, right? So whereas the threshold that you used was 30. So does this mean that these sources were not included, or how?
Yes, I can explain this a bit more in detail. So again, square root T.S. I mean, I think I've explained the T.S. value. So it's a difference in the fit statistics between two models. And then in case if you only have one free parameter, then you can apply Wilks' theorem, and what you get is that then the square root of T.S. actually corresponds to the significance of the source. And this is typically what is used and shown here in the lower panel. So this is a very special case that is called a T.S. map. And the way this T.S. map is, or square root T.S. map, or it's actually a significance map. And the way this is computed is there is a model assumption. And what you do is you assume that there's a point source centered at the pixel of this map. And then the norm of this, or the amplitude, or the brightness of this source is fitted only at the given pixel. And this you do for every pixel in the map. And what you get then is basically like a significance map of the assumption. So is there a point source at the given position or at the given pixel in the map? This is what this map means. And this can be used, for example, to assess the residuals. So instead of showing, for example, the difference between the axis or the difference between instead of showing the difference between the model and the data, in this case, I'm showing the significance or the residual significance that I have. And this is somewhat like a bit more statistically, let's say, like more meaningful measurement.
No, sure. So in case that's a good plot to have. But the thing that confused me is that the sources don't seem to exceed 25 if you go by the scale. Whereas you require the component to be kept in the model if it improves by the TS by 30.
Yes. So what this shows is, this already includes all the significant sources, with the exception, of course, of these shell-like supernova remnant. There we just said, okay, those are excluded from the analysis. We cannot do anything meaningful with those. And that's why they still appear in the residual map.
I see.
Does this make sense?
I think so. So both of those, the RxJ 1713 as well as H.E.S.S J 1614, they're actually not modeled out.
Exactly, they're not part of
You're
of the global model.
Okay, okay, understand.
Exactly.
Okay, so another question, kind of
Mhm.
following up on what David was asking about this
Mhm.
TS.
Mhm.
I assume you're using CSTAT as one of the
Yes, yeah.
And have you looked at the Yella-Castra's square root CSTAT variance estimate to figure out when to figure out what the underlying distribution of the CSTAT could be, and use that as a way to figure out what the cut should be for the threshold?
No, this we haven't. As I said, what we've done instead is that we've done just a Monte Carlo simulation of the source. So we've taken the background as our baseline model, and then we've fluctuated the background using Poissonian statistics, and then we ran like a simplified source detection algorithm on this and verified then somehow like what is the number of false detections that you get depending on which TS threshold you choose. And what we found is somehow like with this TS threshold of 30, we roughly expect like one false detection in the statistical false detection in the whole survey region.
How big is the images typically?
So the whole data set is shown on the slide before. So what you have is roughly a rectangle of 160 degrees by 10 degrees, something like this, or 180 by 10 degrees.
And the binning is by 1 per degree, or
the binning, the pixel size that was used is roughly 0.02 degrees per pixel.
Okay.
So it's like 5 million pixels in the map or something like that.
Oh, right.
Okay.
Yeah, I mean, typically, of course, I mean, one would need to treat somehow like trials in this case, or this is typically what also like other people do. But I mean, with the Monte Carlo simulation, one could avoid this a bit somehow and just say like, okay, this just translates into a false detection ratio for the whole survey region.
Right. No, that's I think that's perfectly legit. I mean, we do that with Wave Detect also for Chandra.
Yeah,
that's how they set the threshold.
Yeah.
Thank you.
Okay.
I just have a follow-up. I'm trying to wrap my brain around the one false detection over the whole survey. That must have something to do with the density. You must have made assumptions about the density of sources or the number of expected sources.
This I have to think about. I mean, like in the method, it doesn't. I mean, typically, I think the difference is the following. I mean, the data that we have is background dominated. So like 90% of the counts that we see in the data, typically like 90% is background, and it's not and it's not sources. And so I think like the common mistake to make then is probably like that a source that you detect comes from a background fluctuation somehow.
Yeah.
And this is what so I think this is probably like the common mistake to make. And then we've just started from the background only model exactly, and then we started to fluctuate it and just like had different realizations of the background model and see like how many false detections just do we get from the background model only. I think this is like the most common, probably the most common thing. I mean, but of course, I mean, one could already see, I mean, there are already systematics also in the analysis. And I think, in fact, probably this number isn't even true of one false detection, but just as a side comment.
Can I ask quickly about what does it mean to have a negative TS value? Is that you fit a source that has a negative amplitude, and whatever the sign of the amplitude is, that's the sign you give the TS?
Yes, exactly. Yeah, I would call this a convention. I mean, of course, like a negative. I mean, of course, you can argue like a negative flux doesn't make sense physically, and it doesn't. But of course, statistically, it makes sense, right? I mean, you can have regions where you overestimate the background or you have like a background fluctuation that goes upward, and then the best fit flux that you get at this corresponding pixel would be negative. And then by convention, and just to make this to make it visible in significance as well, exactly like the sign of the flux is applied to the significance value as well.
Okay, but so then hopefully you never get less than 0 counts in a pixel. Is that some kind of like
no,
requirement?
like no, of course. I mean, like background plus your model is always positive.
That's enforced, or it just there's so much background that always is the case?
There's so much background that this is always the case.
Okay.
Another follow-up question. Two questions actually. One is so when you say when you simulate fluctuations from the background, you're including this empirical diffuse band in the simulations?
This was not included in this case.
Okay, so that could lead you to yeah. So you're actually picking up more sources than there possibly could be. Though of course, you know, you'll be there is also this issue of size of the source, which should matter, right? Okay.
Yes. Yeah.
Another question is, you mentioned spectra. How do you get the energy of the incoming photons?
So the energy of the incoming photons is mostly estimated from. So you can imagine, for if you have an incoming gamma ray in the atmosphere and it triggers this particle cascade, then basically the more energy the particle has, then the brighter the shower is, or the brighter the Cherenkov light is that is emitted by this. And so the energy is mostly estimated from the amount of Cherenkov light that you get within the telescope. So the brighter, the more energy. This is roughly.
Okay, and your and the altitude at which the shower, these Cherenkov showers start is fairly, usually well determined, right? And it's
usually 10,
limited,
something like 10 kilometers or something.
Yeah. Okay. So that's how I mean, so you know the approximate distance. I mean, you know how bright it can be. Okay.
I mean, this is typically determined using Monte Carlo observations, and this includes then, I mean, like with all the complexity, it includes a model of the atmosphere.
Right.
Then to
so
do this.
I'm curious. I mean, do you build an RMF to deal with this? How exactly do you handle that? I guess you will talk about it later when you do talk about gamma pi. But...
Could you just repeat your last question?
I'm just wondering. I mean, do you have like a formal RMF that you use? Or...
Yes.
Oh,
Yeah, I can. Yes, I can talk about this later.
All
exactly.
Right. Yeah. Thanks.
Okay, then just to summarize a few of the main results of this analysis. So in total, then the catalog included 78 sources, of which 64 were reanalyzed in the analysis, and 14 of these sources were just excluded because of this too complex morphology that I've mentioned before. And then what we've done in addition is just like a uniform association of those objects with catalogs from other wavelengths, but typically only based on the position. So we just looked for the nearby sources. And for this, we've used multiple catalogs, for example, like SNR-CAT or Green's catalog of supernova remnants, and also like high energy pulsars from the ATNF catalog. Using this information, we could identify 31 objects. This means those were uniquely associated to one other known object from other wavelengths. Then we had, in addition, 11 dark sources. So those were not associated to any other object at all. And then we had a mixture of 36 not firmly identified sources. So those were associated to multiple objects, and there was just no firm identification possible. What we also found in the data set was basically 50 new previously unpublished sources. With the identified objects, one could even split them into source classes. So typically we found pulsar wind nebulae, which were, I think, 12. Then we had 8 composite objects. So these are a supernova remnant together with a pulsar wind. Then 8 identified supernova remnants and 3 binary objects. So in this, I mean, the binary objects are typically identified on the light curve. So there was no timing analysis done in this analysis, but those were basically already known objects, and we could uniquely say those are binaries. Just a few more HGPS results, and just to motivate a bit, like the upcoming sections on gamma pi and the more advanced analysis methods. So those identified sources are shown on the left side, and we could, for some of those, we could look up the distance, and some of those have a known distance. And what we've done is we've shown, or we've plotted those on top of the Milky Way, together somehow with the sensitivity of the survey, which is shown as a horizon. So assuming a reference source of a given internal or intrinsic brightness, you can assume, for example, whether it was detected by the survey or whether it wasn't, depending on the distance where it is in the galaxy. And this is shown on the left side here. So there's this blue horizon for a source with an intrinsic brightness of 10 to the 34 ergs per second. And then another one for a fainter source with 10 to the 33 ergs per second. And what you can basically see is like all the detected and identified sources are either very close to the sun, and it doesn't really go far beyond the galactic center. So this is already one hint that with this survey, one basically only observed, let's say, like the solar neighborhood. Another way of estimating the completeness of the survey was to look at the log n log s distribution of the sources. So it shows the number of sources above a certain flux threshold. And typically one sees something like a power law behavior for the given distribution or flux distribution. And then one typically sees a break in this power law distribution where where the selection effects start to take over somehow. So where you've missed detections just because the survey was not sensitive enough. And this is shown here on the right side. And then still using the information. So this typically happens in this case with a brightness or with a flux of 10% of the Crab Nebula. This is what's shown here at the center. So the number of detections goes down. And then one can still use this information and this power law assumption just to extrapolate to lower fluxes and somehow estimate like what's the number of sources that you could potentially detect with a future survey, which is more sensitive, and what is like the total number of detected or detectable sources. And we've done this in the analysis, and what we found is that we roughly expect like 400 to 600 sources with a flux larger than 1% of the Crab Nebula in the Milky Way, and that could be potentially detected with a more sensitive and better instrument. And this instrument is already in the planning. This is called the Cherenkov Telescope Array. So it's the same detection principle. So it's an imaging atmospheric Cherenkov telescope, but it just includes much more telescopes in the order of 50. And there will also be two sides. So there will be one in the south and one in the northern hemisphere to really cover the whole sky. Here I'm just showing like a preview. So this is
quick question.
Yes.
About that log and log S code that you have. Do you think that drop off at high fluxes is real, or it's just an artifact of some sort?
Yeah, that one. This one here, I think it's real. Yes. I mean, the way this is measured here, I mean, like for a source to be, let's say, 100% of the Crab or brighter, it would need to be very close. I would say, and it would need to be very, very bright. And I think the assumption is that it would be like if it was bright and very close, we would have seen it.
Okay.
Yeah.
Then
so I think this drop off
is there a drop off? Because I mean, it's simply that the universe can't make things that are that bright.
Our Milky Way.
Or Milky Way cannot make things that are that bright.
It's
right?
not the whole universe.
Yes.
Yes. I mean, it's yeah. I mean, the energy. Let me think about that for a second. I mean, the standard theoretical explanation for this TeV emission is particle acceleration. And I think there's somehow like a trade-off between, so you need a certain time to actually accelerate particles to a certain energy. And then at the same time, there's a competing effect of cooling. So like the particles start to radiate and then cool down. So I think somehow there must be somehow like a built-in, at least, I mean, for the energy of the particles, there must be a limit. And then for the total flux, I guess this depends then basically on, I guess, the region the particles are accelerated in. And I guess somehow for a finite region and a finite acceleration region, you would require somehow that it must have somehow a finite flux, a finite resulting flux.
Right. Okay. Thank you.
So this is the full survey region, and just as a preview, so I mentioned like the H.E.S. Galactic Plane Survey only covered a small part of the galaxy, and one expects just much more sources when looking with the more sensitive instrument. And I've prepared here this visual comparison of the same region that was surveyed with H.E.S. For CTA, so with a more sensitive instrument, and this is basically what it looks like. So it includes the current catalog of sources, and then somehow an estimation on the weaker source population, also including some weak supernova remnants and shell-like supernova remnants which are hidden in the background, and also then like a model for the diffuse emission along the galactic plane. And this is roughly what one would expect. So I think in general, there's a lot of motivation to further continue look into the TeV sky. But also, I mean, with this analysis that we've done, we've already found like a few basic limitations. And those are the ones that I would quickly like to list. I mean, already now, so there's of course a limited angular resolution of the instruments. So for H.E.S., it's roughly 0.1 degree, a bit less. For CTA, it will be better, but still the Milky Way is full of sources, and there are a lot of nearby and confused sources. So source confusion is already a problem for this kind of data. On the other hand, the angular resolution is still good enough to resolve morphologies of very extended sources. And in this specific analysis, just we didn't have a good way of handling it, so we just decided to exclude it. But in general, it would be nice to have something to handle this. Then there's also the effect that these, what I would call like distinct sources or point sources or local sources, are confused with the true galactic diffuse emission, and also like an underlying unresolved population of gamma ray sources beneath. Then there are also instrumental effects. So the instrument response of these IC imaging Cherenkov telescopes vary strongly with energy and offset of the source. This I'm going to explain a bit more detail later. And then there's also just like the requirement to correct the measured sources, for example, for the flux that is contained in this spectral analysis region. As I said, the angular resolution is limited of the instruments. And possibly the spectral analysis region that was chosen for this does not include the full PSF, but just contains like a certain amount of flux that is covered by this region. Then there's also another effect that nearby sources can actually leak into the analysis region of the spectral analysis. And these are all effects that we've tried to correct for in the analysis, but let's say afterwards, and it was not built into the analysis. Then there's another requirement somehow, and this is really one needs to include multi-wavelength information to have a meaningful association of the sources, and also then to combine what we've done in this analysis, to combine these Gaussian components together or back into astrophysical objects and astrophysical sources. So in general, there's really like a requirement for more advanced analysis methods and tools. I would say to fully exploit the existing data, and also then, of course, future data, such as taken by the Cherenkov Telescope Array. And this basically motivated us to work on new analysis methods and software for gamma ray astronomy. And this is what I've been mostly doing since this analysis during my PhD. Okay, And continue a bit now with the analysis methods. We've already covered some more details already by now. But in general, I mean, it's still bin-Pearsonian maximum likelihood analysis and joint likelihood fitting, but extended to more dimensions. So taking into account spatial and energy and partly time information, and also like handling the instrument response in a more general way. This is just the picture from the beginning, and just to make to introduce one convention, so or one coordinate system that is needed to understand a bit the instrument of the instrument response functions for this. So if you take a look at the right side, so the instrument is pointed to a given position in the sky, and then there's the definition of the offset in the field of view of the camera. And then you have the source that you're actually interested in. So this is what's called the offset. So here you can see now a parameterization of the instrument response. These are actually instrument response functions from the H.E.S.S telescope. And first, there is the effective detection area. So it gives the number of expected true gamma-like events per detection area. And as you can see in the image above, so it varies with the energy of the gamma ray, and it also varies then with the offset between the pointing position and the source that you're actually interested in. So this is one of the main ingredients, and then this can be, of course, just multiplied with the lifetime to get something like an exposure definition or exposure map. Those are typically then estimated just from Monte Carlo observations. So one has a model of the instrument, one has a model of the atmosphere, and then one starts simulating shower events and then reconstructs those using the model. In general, this is just required, of course, I mean, to measure the flux and brightness of the gamma ray sources. Then there's the point spread function of the instrument. Again, it varies with the energy, or I could be more specific here. Actually, it varies with the true energy of the instrument and not the reconstructed energy. And as you can see already now, so there is really some dependence here on the right side that shows the size of the PSF defined by the containment radius. I'm not sure if this is a common term, containment radius. So in case, for example, for a Gaussian shaped PSF, the containment radius of 40% would correspond to 1 sigma.
Yeah, we call it enclosed energy fraction.
Okay, perfect. Perfect. And so this strongly varies already with energy. And then it also varies with the offset here. Again, it's just estimated using Monte Carlo observations, Monte Carlo simulations. And typically it is stored just as a radial profile. So the assumption here is typically that it's radially symmetric. So this is one simplification that is made. Also for the H.E.S.S instrument, there's also, there were multiple efforts to describe it, let's say with an analytical shape. What we found fitted well was something like a triple Gaussian or a King profile. But typically one can also just directly work with a radial profile. In general, this is just needed, I mean, for precise measurements of galactic sources and just like precise measurement, of course, of flux of point sources, sorry, flux of point sources. Then there's the third part of the instrument with response, which is the energy resolution, and this is shown here. So typically for imaging Cherenkov telescopes, this is stored as the energy migration. This is what it's called, and this is defined by the reconstructed, or by the fraction of the reconstructed energy over the true energy, and this is shown on the left side in how it varies with the true energy. But then this can be again dependent on the offset, and then for a given offset, this can be translated, and a given reconstructed energy binning that is chosen, this can be translated into an energy dispersion or an RMF matrix, which is shown then here on the right side. So it shows like the typically two effects. So the first one is the energy resolution is just limited, could be approximated with a Gaussian, but then at low energies there's the second effect, which is the bias. So these kind of instruments typically overestimate then or overestimate the energy for low true energies. And this is then taken into account during the analysis to measure precise spectra of the sources, and also mostly like taking account this effect at low energies. Then in the analysis process, then one starts just with the counts. So after reconstruction, one gets basically a list of events with estimated arrival time, position, and energy of the event, and those are then binned into a map. A map here, like in the most general case, is something n-dimensional, but it has a spatial axis, typically defined by some projection, for example, a WCS projection or H.E.S.S projection. And then it can have an additional axis, in this case, the energy of the data. And this is then translated into a list of images or a sky map or cube, however you want to call it. And this is then something, so the spatial and energy binning, this is something that is chosen by the people doing the analysis. Then to do an image analysis, one can basically reduce this case and handle this case just with a cube and one energy bin. And then very similar for a spectrum, one could handle this case as a cube with one spatial bin and an energy axis. But typically in this case, the single spatial pixel has a different shape. So typically it's a circle or any kind of region. And then what one gets out is just the spectrum of the data. Then what's done in addition is that these instrument response functions, for example, the effective area was given in the coordinate system of the instrument. And then in the analysis, this is, or in the, let's say like the preparation part of the analysis, what I call data reduction here, this is projected onto the sky just by evaluating the IF on the given offset and the given pointing position. And this then can be done basically so for each pixel of the map, and also then for the additional true energy map. And then once this is multiplied with the lifetime, so with the time that was spent on this exact pointing position, one gets something like a different, like an exposure, a definition of the exposure. The same now can happen for the energy dispersion, and here's one. So what I'm showing here is already like the very general case. So typically, what I would call like in a classical TeV analysis, this RMF matrix is only computed for one single position for a spectral analysis. But then the generalization of this is to actually compute this for a map, so for multiple positions at the same time. So one would get like a 4-dimensional data structure that has a spatial axis. And then it has an energy and a true energy axis. So it contains like a full RMF matrix for any pixel in this map. And this then gives the possibility to handle really these offset dependence or spatially varying energy resolution in the analysis as well. What is just as a last? This I can explain later. Then the same is done for the point spread function. So again, for the data reduction part, this can be projected onto the sky for a given offset. And again, this can be done for multiple positions at the same time, so one can actually handle then the position-dependent PSF in the analysis. And this is done also just using a 4-dimensional data structure. And in this case, it contains for each position of the map, it contains the radial profile of the PSF, also then varying with energy. And then for the analysis and to compute actually the predicted number of counts from the source, this is then translated, or this radial profile is translated into a kernel or PSF kernel that then can be used for convolution. Taking all this together, this is basically the data model that we use to compute the predicted number of counts for the analysis process. So one starts with a parametric source model. This is the term here on the right side, which can be a spectrum model. It can be an energy-dependent spatial model, And it can also have a temporal model component, but this is handled separately. So the assumption here is that the spectral model can be factorized to a certain degree. Then one just multiplies this parametric source model with the exposure. Then one applies the PSF, and then one applies the energy dispersion to get the predicted number of counts for a given source component.
Just to make sure I'm tracking, so your F source would have been, back on slide 7 or whatever it was, the mixture of Gaussians.
Exactly. Yes, exactly. So the parametric model here could be Gaussian, could be something else. But typically, yeah, it's a Gaussian, or it could be power law in energy. Yeah. Exactly. And this is the data model then that is used to compute the predicted number of counts for the source. And this is then compared using the C-stat to the actual measured data. So this is shown here. So the predicted number of counts minus the observed counts multiplied with the logarithm of the predicted counts. And then this is summed up for all the pixels in the map that one has chosen. And the predicted number of counts are computed as I've shown before, but of course there can be multiple components, like multiple Gaussian components in the model. And this is then really just like a sum over these multiple model components. And in addition, there's something like a global background model or global background estimate. There are some further model parameters sometimes introduced at this stage. For example, the background model that is used can be corrected for some imprecise things. For example, it can have an additional norm, or it can be corrected, for example, in the spectral shape. And then the global fit statistics is computed from that, and then typically this is just optimized using the maximum likelihood approach. There's one more ingredient, or one more step. So, for example, for these image Cherenkov telescopes, the instrument response can actually vary with time. So one can easily imagine that that the atmospheric conditions, for example, change fast or rather often. And the assumption here is that they're typically stable for this half an hour. But then to treat these varying observations conditions, what one can do is one can use a joint likelihood approach. So actually this likelihood is computed only for one observation of the same astrophysical object. And then the same astrophysical object was observed at a different time, but with different observation conditions and different instruments response functions. And then again, the likelihood is evaluated for this case, and then the likelihood is multiplied on just for these different observations to get something like a global likelihood. And this way, then one can treat like the varying observation conditions more correctly. This is one use case of this joint likelihood approach. Another one is, of course, one could combine data from different instruments that have different instrument response functions. In this case, for example, one could combine Fermi-Lat data with CTA data, or Fermi-Lat data with H.E.S.S data. This is somehow like the most general analysis approach that we use, and this is implemented now in a package that we created or started creating a few years ago, which is called GammaPi. And what we've done there is this was very similar to a time actually when the AstroPi project started. So it turned out somehow that Python was like a very good language for data science and data analysis in general. And there were all these packages around that could be just used to build somehow a gamma ray data analysis package. This slide I'm gonna skip, but we can maybe come back to it later. So this is what we've chosen then for GammaPi as an approach. So GammaPi builds on the AstroPi library and SciPy and NumPy libraries to implement this basically the standard analysis method that I've shown before. Then there are a few additional dependencies which are not that important. But what we've tried for GammaPi was also to implement somehow like a uniform fitter interface, and so there can be multiple backends that actually do the optimization then One standard backend is for example, IMINWE. Another one that we call into just because we've made good experience with it is Sherpa. But it can also be, for example, connected to an MC sampler. So there's one prototype in GammaPi actually trying this. GammaPi is openly developed on GitHub, so I've put the link here. And it uses what I would call like a standard multi-branch GitHub workflow. So new features in the package are developed on the side, and then they're merged in the via pull requests into the master branch. And then each of these pull requests is typically reviewed by a more experienced developer. What we've also set up is a continuous integration system. So there are tests for the software, and those are run continuously also on each pull request, just to make sure that any contributions or new pull request does not break anything of the existing functionality. If it does, then we have a chance of understanding why. Then we have also like an automatic building and deployment of the documentation. So I've put here a link to the GammaPi documentation, where of course like much more details on the package are documented. And we also have validation and benchmarks which are run daily. These are just a few more implementation details. So we're using testing and really like documentation for the software regularly. We also have developer meetings and co-working days. This is what I've done, for example, in the past few years. So I've organized and led those GammaPi developer meetings. And currently we have like an active developer base of, let's say, like 5 to 8, or sometimes 10 people. Currently, there are only minor versions of GammaPi, but we are working towards a long-term stable version and a 1.0 release of the software. Here's just a very quick overview on the API of GammaPi. So I've already mentioned in the analysis method. So one starts with these gamma-like events, then the data is binned, and then one uses maximum likelihood fitting to get some science products out of the data. So things like source catalogs and flux maps or TS maps that I've shown before, and SEDs and light curves. And this is mapped then in the GammaPi API. So there are packages like data access, there are packages like makers for this data reduction process. And then there are package called data sets, which then bundles the data together with the instrument response functions and evaluates the likelihood. And then there are the package that, or the sub-packages that do the likelihood fitting. So there's one package called GammaPi modeling, which implements the fitter interface, and also like multiple models like power laws, Gaussians, shell-like models, and in general, it's just like parametric models to model the data. Then there's another package which is called GammaPi estimators, and this helps then and implement standard algorithms for flux point estimation and flux map estimation and light curve estimation, and things like this. I want to conclude just with 2 application examples of GammaPi. So one here is to combine data from different instruments, and this was an analysis that was done by Cosimo Nigro et al., and we have contributed. And this was a proof of concept that actually multiple or data from multiple instruments can be combined. So this used data from the Fermi-Lat instrument, it used data from the H.E.S.S telescopes, and it used also data from other imaging Cherenkov telescopes such as MAGIC, VERITAS, and FACT. And it has done just a one-dimensional or spectral analysis of the Crab Nebula. And the interesting conclusion here is that certainly just by taking more data into account, one can improve a lot on the statistical error of the measurement, and this is shown here on the right side. So this shows the likelihood contours or the error ellipses for the 3 parameters that were fitted for this spectral model. So the model was a log parabola, and then with the colors, different colors here shown, first the measurements of the individual instruments, and then in red is shown the combined measurement of combining all the data from different instruments. And of course, one can see that like the error of the measurement is much smaller. And this is true for, in this case, the correlation between the flux and the spectral index, the flux and the beta and the alpha and the gamma and beta parameters for this log parabola. So the main conclusion here was really that it's expected, but it was also shown that just like by combining data, one can really improve on the statistical error and also get like smaller correlations between these spectral parameters that were fitted. Then here's just another little application example. So what I mentioned, for example, in this H.E.S.S Galactic Plane Survey analysis, there was just the approach of measuring the spectrum in a given region and then fitting the power law. But now with gamma pi and having this, what I would call like spectromorphological measurements, so taking into account the energy axis of the data, one can actually do something like fitting the PSF directly and estimating the spectral model like this, and also taking into account the energy dependence of the PSF. And there would just like to show two effects. So here on the left side, this shows that the significance of the source and the sensitivity of the measurement for the 1D case, it depends on the size of the region that is chosen, just because it can be like the PSF cannot be, or in some cases the PSF is possibly not fully contained in the analysis region. And there's somehow like an optimal region size that one has to choose for a 1D region. And in this case, for this little mini study that I've made, this is roughly, I think, 80% of the containment of the PSF, where one gets like the maximum significance of the data. And this is then like an effect that is naturally accounted for if instead of doing the analysis in a certain region, the full PSF model is fitted to the data. And this is shown here on the right side, where those two approaches were compared. And in general, like one gets a bit more sensitive analysis, just because, I mean, the more information is taken into account, and effects such as this leakage of the PSF is naturally corrected for. In addition, just as a side comment, this also offers them the possibility to, for example, separate close by point sources based on the spectral information as well. Okay, let me come to my summary. So in general, this H.E.S.S Galactic Plane Survey showed that gamma ray astronomy is entering, let's say, like the era of catalogs. So gamma ray sources are not treated as individual phenomena, but really they are populations of gamma ray sources in the Milky Way and can be studied this way. However, these classical gamma ray analysis methods, so limited to just fitting a spectra, a one-dimensional one, or just doing the analysis on an image, are not necessarily sufficient to deal with all the challenges of the data, such as source confusion, and also like these complex varying IIFs, so IIFs varying with energy and offset. And really like a more complete way to treat the spatial and spectral information simultaneously is then really like this combined spectromorphological analysis, or 3D or cube analysis. Then another conclusion is that like the statistics, of course, and energy range of measurements can be improved by combining data from different instruments. And this is also something that is implemented in this gamma pi package. And one can really improve then on the statistical errors and constraint of the spectrum models. In general, there was really just like a requirement of analysis software that implements this functionality and makes it also available to a larger community of gamma ray astronomers. And this is why this gamma pi Python package was created. The package now is actually a candidate for the CTA science tools, but hasn't been chosen and decided yet. There's one little outlook. So this combined spectral and spatial analysis is not yet available since a long time in the gamma ray community. So right now there are not many studies published with this yet. However, there are a few studies that are being worked on that I will mention below, just to excuse me. Okay, so yeah, scheduled the next gamma pi release before. So just to mention, so gamma pi is still in development, but it's but we're planning actually to release a 1.0 version of the package rather soon, along just with a paper describing the software. What's currently been done with the Gamma Pi package is that existing H.E.S.S measurements and existing H.E.S.S data is reanalyzed using this combined spectral and spatial analysis approach. And this also gives like a simpler solution or natural handling to study effects like energy-dependent morphology of gamma ray sources. And then Gamma Pi is the candidate for the CTA science tools and is already used for simulated CTA data, such as the CTA Galactic Plane Survey. In general, then Gamma Pi is also evaluated for use in other imaging Cherenkov telescopes, such as Veritas and MAGIC, but currently no publication has been made for this. And also some work that I've started with colleagues in Heidelberg is also to evaluate the use of Gamma Pi for ground-based water Cherenkov observatories. So there's a whole different approach to studying TeV emission, and this is the water Cherenkov approach. And one instrument of this kind is, for example, HAWK. And in general, this opens up like the possibility for many future combined measurements using Fermi-Lat data, H.E.S.S data, Veritas MAGIC data, and also possibly HAWK data, and just increase the statistics and the energy range of existing measurements as a whole. That's it from my side. I realize I think I covered a lot of topics, and I think like we've clarified a bit like the details of the analysis beforehand before I actually got to it. But let me know if you have further questions.
Yeah.
Thank you, Axel. Nice talk.
Yeah, thanks. Yeah, you were interrupted many times, I guess.
Yes. I guess we should ask for questions before we jump in.
I think, yeah.
Are there any comments, thoughts from other people?
Can you go to the slide with the combined different telescopes looking at the crab?
Yep. This one here. Mm-hmm.
Yeah, I thought this was a really cool thing to be able to combine the likelihoods for all of them. Is there any work on like using this to actually calibrate the different telescopes? Like some of these contours, they're not overlapping. Does that mean that you could somehow use this, like, I don't know, maybe the H.E.S.S energy bias is wrong in the Monte Carlo or something? Or is there some way to like have all like nuisance parameters that can calibrate the individual telescopes?
This is actually what has been done exactly in this analysis as well. I'm just not showing it here in this case. So I think there was a second analysis exactly using this data, and then introducing nuisance parameters for the energy scale and the energy estimator of the different instruments. And this then I think was there was some prior information on like what's the actual position of the energy estimator of the different instrument, and this was included then in the second analysis as well. And then there was, I think, this nuisance, exactly like I said, like this nuisance parameter on the energy scale, together with a prior. And this was exactly done in this analysis. I'm just not showing it here. That's it.
Oh, okay, nice.
Hi, quick question. So you might have talked about this, but I joined late. So did you talk a little bit about anything about computation? Or I know in practice, fitting large-scale Poisson models can be a hard task because these models are hard to work with. They have likelihoods that are just non-Lipschitz, and they can just blow up and everything. Is that an issue in your case? Can you talk a little bit about the computational aspect?
Yeah, I think there are some aspects to it. I mean, typically the fitting and modeling of the sources is done by hand. This is just what's typically done by the people doing the analysis. So you make a choice on the morphology of the source. You make a choice on the spectral and the spectral shape of the source, and then you run the optimizer, and then you try different models, and then you just see what what you get as somehow as a best fit model. But indeed, I mean, you cannot be sure somehow that that's really like your global best fit model. And my short answer to this is typically that's just how it's done. It's done, let's say, on a best effort basis. So you try multiple models, you possibly try different starting parameters. But right now, I think there's no standard way, for example, I mean, one could do something like a grid search, but at this point, of course, it gets very computational costly. So I would say typically it's done on a best effort basis.
And is it because the model is not convex? It is like irregular, or?
I mean, typically, I mean,
approach.
I mean, of course, the close to a minimum. I mean, the likelihood shape or the shape of the likelihood surface. Locally it is convex. But then, as I said, I think there's currently, as far as I know, there's no way, let's say, like to estimate or make sure somehow that you've arrived at the global best solution. And the only way I think you can come around with that is just to try variations. Right now.
Got it.
As far as I know, as I said, I think there's no standard way of treating this. So it might easily happen that maybe the fit converges but gets stuck in a local minimum or something like this. And the only way right now to overcome this is just to try different approaches by hand. This is and then you describe it and just say like that's what has been done.
Got it. Thank you.
No, this is three-dimensional fitting. I mean, this was so you do actually have the model, which is 3D model, right? Spatial and spectral model when you fit. So that's not trivial to fit. That's right. Yeah.
Yes, I mean the assumption that is, or how it is handled in GammaPy right now is. You typically factorize the model. So you say there is a spatial part and there's a spectral part. And the spatial part does not vary with energy. So we assume that the morphology of the source is constant across all energy bins. And this, of course, reduces then like the number of parameters that you need to introduce. This is typically what is done. So for a point source, then you get the position typically, and then if you have a power law, you get the spectral index and flux. So you have typically for a point source 4 parameters that you optimize. But of course, then for more complex sources, like even for Gaussian, then if you assume that it can be extended in a certain direction or can be elongated in a certain direction, then of course you get much more parameters. And I think this is in general, right now, this is typically used for individual analysis of sources, but I mean, it certainly gets a problem once we start to analyze CTA data with a deep exposure in a certain region, and you have like 10 or 20 sources that you have to model at the same time. And I think for this right now, I think there's no straightforward strategy to optimize the parameters. Yeah.
So I'm slightly confused. So when you do the multiple instrumentation thing, so do you use the same data cube approach, for example, for me and all the other instruments that you outlined for H.E.S.S? Or is it
yes? The short answer is basically yes. So in this specific analysis that I'm showing here, this was just done for a spectral analysis. But this approach can be extended to this 3D approach and the cube. And I think, in fact, I mean, this whole or the combined spatial and spectral analysis was mostly inspired from Fermilab. I think they have introduced this for the first time in gamma ray astronomy. And then this model was applied, or the data model and also the analysis procedure was also applied then to H.E.S.S data and the other instruments. And this is currently where it is. So I think for H.E.S.S data is already available and it can be analyzed in this way. But typically then you can do it the same way for all the other instruments. For example, for Hawk, it can be basically done the same way. So can also use this 3D cube for Fermilab data anyway. For other instruments like MAGIC and FACT, this does not work, just because they don't have they don't know the instrument response, how it varies, for example, with the position and the offset. So in this case, it only works with the spectral analysis.
So essentially, what you're doing is the equivalent of what we would call a joint spectral fit. Is that a fair characterization?
Yes. In this specific case, it is. Yeah. Okay. And then it can be even extended to morphology analysis and fitting a morphology model. But so far, this hasn't been done yet. Yeah. As I said, I mean, we're just providing the tools for this.
And when you do joint morphological spectral analysis, with essentially the 3D cube. So do you understand? Is it so you're assuming that each Gaussian component has the same spectrum, right? So but then different components could have different spectra. Is that how you're doing?
This is just to clarify. I mean, this is something that hasn't been done yet. This is just something that would be possible using gamma pi and using the tools. Okay. And in this case, of course, you have the freedom to set a different spectrum model for each component that you have in the model. Yeah.
Okay. Got it.
Yeah. Well, I think it's late. We probably need to close.
Yeah. Yes, it is in fact. Yes. So we should thank everyone for joining. But of course, please, Axel and David and Thomas, stick around for a bit longer.
Yeah, for a little bit after the talk.
3 minutes.
And Charlie, yes.
No, Charlie, I think Charlie had to go.
Left,
yeah, because he had to go to the dentist.
Right.
Anyway, stop recording.
Oh, right. Yes, thank you.
I think that's what